Good evening, everyone. So today,
Good evening.
we're we are in the ninth problem solving session for this course, Aqueous Corrosion and Corrosion and its control. So we have last week's assignment to discuss. So we can start with that. The first question is, due to autocatalytic nature of crevice corrosion, the pH of the crevice becomes. So you remember this lecture slide. What happens in the crevice corrosion is you have a glass plate on the top. The crevice forms underneath the plate. So due to limited diffusion of oxygen, you're not able to attain passivation inside the crevice. So remember this plot. So to attain passivation, you need to cross the critical current density uh, for the corrosion reaction. So in the crevice, due to limited diffusion of oxygen, you are not able to cross the critical current density. I see. So that's why passivation doesn't happen inside the crevice. So what happens here? Sorry, corrosion is taking place. So your metal is forming metal ions, and that metal positive ion is reacting with the water, giving you H plus ions in metal hydroxide. Okay. So since generation of generating H plus ions, so your pH is decreasing. So becoming acidic. Autocatalysis, it means that as the pH decreases, the corrosion rate increases further. So corrosion is added, so forming a kind of positive feedback loop. Okay. Next question. So which of the following additions to 3.58% NaCl will show highest pitting susceptibility for 316L stainless steel in that solution? They're given E naught for iron, for tin, and for silver. Okay, so yes. The tendency for pitting. So we're just looking at which is the most strongest oxidizing agent. So we just have to look at the delta E values. So E naught for Fe plus 3 Fe minus 0.3037 Not for Sn plus 4 to Sn is plus 0.0135. So this is more oxidizing than ferric ion, where Ag plus Ag has plus 7.996. This is even more oxidizing. Since this is the most oxidizing, this will have the highest susceptibility for corrosion. So it will see. The third question was pitting tendency of a metal increases if its absorption, declaration potential automatically is high. Repit is high, repassivation potential is high, surface is rough, surface area of the sample is low. So, there, shall we have this nuance diagram? This is a critical current density IC. E-bit. This is a repassivation. E- so, this is your high passivation. So equilibrium potential of the metal is high, so this just means where this Evans diagram the your metal lies. So I think in the solution they haven't mentioned it, but I feel that this should be a correct answer. If it's closer to the E pit, equilibrium potential is high, it will be closer to the E pit value, and uh, its fitting tendencies will increase. Mm, okay. Uh, and if E pit is high, so it's for something higher, your fitting tendencies will decrease. So this should increase fitting. This will decrease. Means repassivation potential is high. So if the repassivation potential is high, it's yeah, it reduces fitting. This will also decrease surface roughness. This increases fitting. So I think this was covered in the lecture. Mm, I think he talked just verbally in this point. Surface nature. If it's smooth, you'll see less amount of lesser fitting. And the surface area of the sample is low. So this also reduces fitting. So this fitting is a probabilistic mechanism. So where the pit will form depends on how much surface area you have. If you have larger surface area, you'll have larger probability of finding a defect or site where pitting will start, initiate. So I feel like A and C, D should be the correct answers. Did you guys have any like counter argument? Like why A shouldn't be? I feel like A should be the answer. If you all mark this answer, I'll ask the NPTEL to correct the answer solution. Um, okay. Uh, and also like should I do it? Someone should post it in their forum. So the other TA maybe she can correct it.
So is there any issue in the solution of the question?
Uh, in the third question, they've only given surface roughness as the correct answer. Shouldn't the first option also be correct?
For equilibrium potential, if it is high, the metal will pose as a more noble. Fitting will not increase in that case, sir. If it is more noble, then fitting won't. Fitting will increase in case of passivation is there. If a metal passivate oxide layer deposits on the surface, then it will fitting tendency
Mhm.
will increase. And if the metal goes noble, noble means it is immune to
Okay,
corrosion.
it's talking just about the nobility of the metal,
Yeah, it
right?
is talking about the equilibrium potential is high, means it's going towards noble. It's not talking about passive layer.
Okay, I thought it was talking about this diagram and where it lies on this curve. Yeah, if it's more noble, it'll have lower fitting.
More the noble the metal is, the less chances of pitting will be. Pitting
Yeah,
happens
yeah,
in metal passivates.
yeah. Maybe that's why it's decreasing. So I thought it was talking about this curve. Never mind. Okay, which of the following stainless steel steels show the highest pitting resistance? There we just have to calculate the Prem number. So, uh, yeah, So this is your prime number, and so percentage CR is 3.31 into percentage molybdenum plus 0.5 into percentage tungsten plus 16 times percentage of nitrogen. So for the first one, which is Ap20 nickel 25 Cr and 0.1 nitrogen. Here prime number becomes 25 plus 3.1 3.3 into percentage molybdenum, which is 1, tungsten 0 plus 16 times percentage nitrogen, which is 0.1, becomes 2.5 plus 3.3 plus 1.6 and 15. Um, 6, 7.5, oh, 25, 9, 29.9. For the second one, we have Fe10 nickel, 18 chromium, 2 molybdenum, and 0.2 nitrogen. So again, the number becomes 18 plus 3.3 into 2 plus 0 plus 16 into 0.2, 18 plus 6.6 plus 3.2, 8, 27.8. Okay, so this has higher prime number, so between these two. And in the last one is Fe10 nickel, 25 chromium, and 1 nitrogen. So here, yeah, and comes 25 plus 3.3 into 0, 0 plus 16 into 1 plus 25 plus 16, so it's 30, 41. So, yeah, this has the highest prime number, so this is uh, has the least repeating tendency. So higher your prime number, repeating tendency is lower. Therefore, I can say the material C has highest splitting resistance. Okay. The following statement is incorrect here. Teflon gasket inside Teflon gasket is inferior to asbestos gasket in lowering the revised corrosion rate in metals. Okay, let's see first one. The lecture. Slide mentioning the surface roughness point. Small surface was shows better with lesser facility. Top skates. So what's happening is asbestos is able to absorb some water. So when you have water, it will have corrosion. Whereas in Teflon, it's uh, it doesn't have water sealed inside the gaps. So it provides better um, cor- provides corrosion resistance. So if you just assume this is your gasket, asbestos will have microscopic, like small pockets of water inside it where the reaction will take place and cause corrosion. As in case of uh, Teflon, mm, it won't absorb water and yeah, prevent corrosion. So this is incorrect. This is incorrect statement, so this is the right option. 317 stainless steel, Fe18 Cr10 nickel or molybdenum. Steel better resistance than the copper zinc alloy. So I think this one we provided in the lecture. Lecture 18, slide 3. So more corrosion resistant metal becomes more susceptible to crevice corrosion. As stainless steel is prone to crevice corrosion, whereas uh, the 7030 copper nickel alloy is not prone to crevice corrosion. And this statement is incorrect. Since this statement is incorrect, so this is the right option. Again, 317 stainless steel, the same stainless steel is resistant better to vice corrosion than 316 stainless steel, just lower molybdenum. So effects of different alloying element, what happens? So addition of chromium, molybdenum, nitrogen, tungsten, silicon, vanadium, nickel to the stainless steel increases your EFIT, thus reducing corrosion, device corrosion tendency, giving better protection. Your molybdenum, nickel, nitrogen, tungsten, chromium also increases your reactivation. So again, this increases your uh, prevents device corrosion, and chromium, nickel, tungsten, nitrogen, they reduce the passivation current, so it will also slow down the corrosion, since you're reducing the passivation current. And uh, these elements, chromium, nickel, molybdenum, nitrogen, vanadium, they also reduce your uh, I critical. So if I critical is lower, it's easier to passivate. So just if metal has something like this, and inside the pit you are some in the active region, in this region somewhere over here, suppose you're here, so you won't have passivation, whereas in this alloy you cross the critical current density and you'll attain passivation. These are the effects of different um, metals. So molybdenum, as you see, is increasing, improving device corrosion resistance. So more moly is better. So the statement is correct. So this option is not correct answer. Okay. So we have question 6, which is in fitting. On what factors is the fitting tendency of a metal is function of what factors? Option chloride concentration, pit depth, applied potential, and melt. So just see this name. Yes. For the first one, uh, for the first one. Okay. First one, yeah. So your more aggressive ions, uh, more aggressive ions like chloride increases your pitting tendency. So will cause more pitting. So yeah, and that's what was happening in the pit. Like if you remember, you had your glass slide pit. Okay. So it's inside your pit. What's happening is metal is dissolving. Will form metal plus electron. This metal ion is reacting with that water, giving metal hydroxide plus H plus. Since your pit is positively charged, you have H plus ions inside. It will attract chloride ions from nearby region inside the pit to balance the uh, charge. So this chloride ion further attacks the passivation layer, increasing the pitting. So yes, pitting is function of chloride concentration, pit depth. So as you're increasing the pit depth, your uh, pit is becoming more stable. The environment, if it's uh, further, if the pit is deeper, the environment inside the pit will be remain stable and more acidic. It will let less disturbed by flow or through diffusion. So path is longer, it will take longer through diffusion. So it remains more acidic and the pit chemistry is maintained. So yeah, so if pit depth also affects your pitting tendency. Here they're talking about professor talking about the uh, criteria like if the pit depth increases too much, the resistance for the electrons from the pit to the surface increases. So if it's very deep, so your the resistance between for the electron transfer becomes too large and thus giving not pit stability. It's talking about pit stability, yes. So radius is larger. I think he was talking about the diffusion of H plus, not the electron. If you have sufficiently large current, it's function of R and S. Okay, applied potential. Here you need to see your Evans diagram. Okay. So as you apply different potential, you're going closer to the pit, right? Apply different potentials. You're moving. If you go apply higher potential, so it'll move closer to pit value and become more susceptible to pitting. So yeah, applied potential also changes your pitting structure, pitting tendency. Okay. Next question. Last question for the assignment. Two similar samples with identical crevice geometry is exposed to flowing 3.5% NaCl solution and stagnant 3.5% NaCl solution. Which is correct? Second one is stagnant, first one is flowing. So here again, your device is sensitive to metal corrosion, you'll have acidic environment inside the crevice. So if it's stagnant, this crevice will remain stable and will have higher concentration of metal, sorry, H plus ions and lower pH. pH is low, and low pH, so this will increase corrosion. So this will happen in stagnant condition, and whereas if you have flowing condition, what will happen is you'll have lesser number of H plus ions inside. So these H plus ion will get washed out by this flowing water, the flowing solution. And yeah, since here the relatively pH will be higher in this case. So pH is higher in this case, so this will have lower corrosion. So sample two, second one, first one, sample two will have, since this is lower pH, and corrosion will be more. Lesser corrosion. So since this has more corrosion, it will fail first. So now in the case of second will fail first. That was the logic behind this one. So, okay, still have a lot of time left. And do you guys have any questions about this assignment? Like you didn't understand the I can explain again. If not, if you have any questions regarding the next assignment, you can ask. I can try to answer it, or if I'm not able to, I can have the answers in next session. Assignment 9 and due on 2nd April. Other questions? Lifeline attackers. Lifeline attackers. Stabilized stainless steel is more. This is all related to your chromium carbide solution, capacitors, and chromium carbide. Lifeline attacks, just to see where you have more precipitation chromium carbide.
I think brass.
I think there are multiple options. So.
Okay.
We can discuss this more. Mm, Intergranular corrosion in austenitic steel would occur, would not occur. I think they're all covered in lectures.
Question 3.
Question 3. Sensitization of austenitic steel depends on what factors? So, sensitization of austenitic steel depends on multiple factors. If it has tendency to form chromium carbide precipitate at the grain boundary, which will lead to chromium depletion, which will thus cause intergranular corrosion. So, temperature, only temperature it doesn't, composition also affects it. Temperature does play a crucial role, but other factors like carbon content and other stabilization elements also affect it. So this is not the only, since it's mentioning only temperature, that's not correct. On to the type of grain boundary. The nature of grain boundary is high energy grain or low energy boundaries that will affect carbide precipitation. So I think this should be correct type of grain boundary. It will like affect your carbide formation. Addition of stabilizing element. And this should depend like elements like titanium form more stable carbides instead of chromium preventing sensitization. And carbon content, yeah. So if you have higher carbon, you will have more carbide formation, thus increasing, you will consume more of your chromium and thus increase your susceptibility for interthermal reaction. This should also be correct. So I think only last three should be correct, right? But I'll you can look at previous answers and solution and discuss this assignment more in next class. How many questions here? Oh, 11 questions. But none of them has anything, any numerical. It's all theory-based questions. Okay. Mm, Any questions from this week's lecture videos? Mm, mm,
To understand each and every point, then only you can understand the answer to question. That is the
yeah.
problem.
Okay. Yeah, even I have to. I didn't get chance to look at all three videos this week. So I don't know what portion was for what. So question 6. You mean from this assignment, last week's assignment, or the current assignment it is due? This one? Assignment 7. Okay. 7. Sixth question. Which of the following statement is true for integral corrosion of stainless steel having similar carbon content? Okay. If they have similar carbon content, I think then diffusion of carbon would play a role. Solubility, like in ferritic stain steel, they have low carbon solubility. So they rarely form chromium carbides and are generally resistant to integral corrosion. Duplex steels. Are acceptable. Um, they are stabilized, or they have lower carbon variant, then they are actually less susceptible to also. It depends on the variant of austenitic steel. But usually, since austenitic steel have higher carbon content, they'll have higher chromium carbide precipitate in the real boundaries. It should lead to higher uh, intergranular corrosion. Ferritic हो गया, Martin's Martensite. Again, Martensite. Does Martensite have higher carbon content? The- uh, Austenite usually has higher carbon content compared to ferrite. What about martensite? They're usually formed by rapid cooling of austenite, resulting in supersaturated solution of carbon ferrite. Again, they should have higher concentration of carbon, so they should be more susceptible. I think you just have to look at but the question says they have all similar carbon content. Okay, I'll have a look at the videos, and I think it should be like diffusion of carbon that should play a role. Different steels will have different amount of different lattice size, and then that will hinder or promote diffusion of carbon. The one which has higher diffusion will chromium will the carbon will reach the chromium button, forming the precipitate, reducing it to chromium, promoting internal corrosion, right? Yeah, we can discuss this. I'll have a look in the next session. And I think this assignment is completely based on intercarbon corrosion. We can end the session.
Okay, right. Thank you.
Yeah, okay. Thank you for joining.